Here is Spring 2019 Midterm 2 for MA 262. Question 1, we're considering the following two matrices and finding the determinant of A cubed times B inverse. So let's apply a couple properties of determinants that we know. We know that the determinant of A times B is equal to the determinant of A multiplied by the determinant of B. We can use this together with the fact that the determinant of B inverse is equal to is equal to 1 over the determinant of B, to rewrite all of this as the determinant of A multiplied by the determinant of A multiplied by the determinant of A, because really this A cubed is just the determinant of A all over the determinant of B, or the determinant of A quantity cubed over the determinant of B. Okay, so now that we've got that out of the way, we know that what we're plugging into in the end. I'll just leave that there, and we can go solve for the determinant of A and B to plug those in later. So they're being a little bit kind to us in A because we have a row with only one element in it. We have this 2 all by itself. And if we take note of this special sign matrix here, plus, minus, plus, minus, plus, minus, plus, minus, plus, we can rewrite this determinant by kind of factoring out this 2 and then crossing out the row and the column that that 2 is in and multiplying it by the determinant of what's left. But we have to be careful because when we factor out that 2, it has to come with the sign of the position it corresponds to in this matrix. So we will end up with the determinant of A is equal to -2 multiplied by the determinant of what we get when we cross out A's row and column. So -2, -1, 1, 1. This gives us -2 times -1, which is just 2. Yeah, okay. So there's our determinant of A. We know that the determinant of A is 2, so we can go replace our numerator with 8. Perfect. Now for B, it's a little more tricky. We'll just do the lazy way and do the full expansion of this determinant by cofactors. So that will be 1 times the determinant of this matrix right here, minus 1 times the determinant of that matrix, plus 3 times the determinant of that matrix. It's just like the cross product, but instead of ijk, you have 1, 1, and 3. So we have 1 multiplied by 2, 1, 1, 1, minus 1 multiplied by -2, 0, 1, 1, plus 3 multiplied by -2, 2, 0, 1. Let's evaluate all of this. Here we just get 1. Here we get -2, so plus 2. We have a running total of 3. And then this gives us -6. So overall we get -3 as the determinant of B. We can plug that in down here, -3, and our answer is D. Let's check that. Let's check that against, sorry, why did I say D? We got -8 over 3. That's C, and that is our correct answer. C for number 1. Question 2, let's find all the values of K such that, never mind, it's not such that, so that these 3 vectors form a basis for R3. So 3 vectors are a basis for R3 if and only if they're reduced echelon form. When we smash them all together, it has 3 pivots. So 1, -1, 0, 2, 0, 1, 1, K1. Or you can think about it as we have a pivot in every row or a pivot in every column, or you can go a little bit higher level and say that these 3 vectors are linearly independent. So let's solve for when this happens. Let's add row 1 to row 2. We will get a 0, a 2, and a K plus 1. And then, well, we're actually pretty much done. Let's divide row 2 by 2, and then we'll see that we definitely do not form a basis for R3 when these two rows are equal to each other, right? Because we can use one then to set the other one equal to 0. And a 0 row means no pivots for us. So, but that will only occur when k plus 1 over 2 is equal to 1 for those two rows to be equal. So solving that, we see that that occurs when k is equal to 1. So this works perfectly fine as a basis for R3 so long as you can't do this and set one row equal to 0, which only occurs when k is equal to 1. So D is our answer for number 2. Number 3, this is a subspace of R4. We're finding the dimension of it. Okay, so this is a little bit of a weird thing to wrap your head around, but I hope that this explanation, helps a little bit. Let's walk back and use a slightly simpler example, then a slightly more complex example, and then we'll work all the way up to this one. What is the dimension of x equals y? Well, what's that graph going to look like? It's just going to be, whoops, that's kind of crappy. It's just a line through the origin, right? And lines are one-dimensional. So this is one-dimensional. Let's move up a step. What is the dimension of x plus y plus z equals 0? Well, this is, I've kind of made this hard on myself by drawing the first octant like this, but it's a plane. It's a plane in 3 dimensions, and what's the dimension of a plane? The dimension of a plane is 2. Maybe you're seeing a pattern here. Note that we could also write this as x minus y is equal to 0. And so really, the dimension of any subspace that you can express in one big equation like this is just given by how many variables you have on one side. They're just set equal to another variable. And what that's really doing is saying, if we go back to this example, okay, your x and y can change as much as they want. You can do whatever you want with x and y. In a sense, they're free variables, but z has to compensate for whatever kind of mistakes or not mistakes, but whatever changes you make with x and y, you have to compensate for them with z so that the whole thing is equal to 0. And so really, the only dimensions you have free reign to move through are these two right here, x and y, and z will adjust to compensate. So just the same kind of thing happens up here. A, B, and C can change all around. You can do whatever you want with those three, so long as B comes in and picks up the slack to compensate. So as a result, this trend will continue when we add another variable. This thing is 3-dimensional. It's a 3-dimensional shape or area in 4 dimensions, which is, we really can't think about that too hard or else our minds will explode. But there we go. That is our answer. That is D for number 3. Hope that makes sense. Question 4, let A be a 4x5 matrix and B be its reduced echelon form. Which of the following statements must be true? So we have 4 down, 5 across. So our matrix is wider than it is tall. What is true? The pivot columns of B form a basis for col A, the column space of A. So this is so close. This is so close to being true, but it's not true. Because remember, the pivot columns of B are reduced echelon form. Just tell us which columns of A form a basis for the column space of A. So you don't row reduce things and then pick those pivot columns out from your reduced matrix as your basis for your column space. You have to go back and look at your original matrix A. So this is very close, but not any good. What about 2? The non-zero rows of B form a basis for the row space of A. So you might be quick to say that, this one should be false for the same reason that number 1 is false, that, we have to go back to A and correspond the pivot rows of B with the rows of A, which will then form the basis for the row space. But the thing is, The only reason that we need to go through that whole process when we're finding the basis for a column space, like we were talking about in 1, is that row operations mess with the column space. But row operations, the normal elementary row operations that we're used to, have absolutely no impact on the row space. And that kind of makes sense. All you're doing is scaling, exchanging rows with each other, and nothing really happens column-wise. Now, that explanation really doesn't work, but I hope you kind of sort of get what I'm saying. So because row operations don't change the row space, the reduced echelon form of a matrix has the exact same row space as the matrix that you as the matrix A that you reduced down to get to matrix B. So this is perfectly valid. And you should also note that the non-zero rows of B is the same thing as saying the pivot rows, because if we have an echelon form here, the only rows with pivots in them are going to also be the only non-zero rows. The only way we don't have a pivot is if we end up with a row of all zeros. So that is in fact true, but for a really weird reason. 3. The rank of A could be any integer from 0 to 5. Well, okay, let's test that. How are we going to fit 5 pivots in here? Let's try. I've added 1 pivot. Okay, we have 3 rows left. Another pivot, and another pivot. Wait a second. We've added 4 pivots, but there's no space for another pivot. We have 4 rows full of pivots. I can't go down another row to add another pivot. So no, our rank is limited by, in this case, the number of rows that we have, because the number of rows is less than the number of columns of our matrix. So 2 only is correct for number 4, and that is B. Yep, good. Question 5, we have a matrix A here. We're finding the product of all of the eigenvalues of A. So finding our eigenvalues, we are going to substitute negative lambda in on this main diagonal. So we have 1 minus lambda, 0, 0, 2, 3, 2 minus lambda, 4, 6, and 4 minus lambda. And like we do with all of our determinants, if we're finding the determinant of this and setting it equal to 0, which is really what we're solving here, we're solving the determinant of a minus lambda I equals 0. This will give us our eigenvalues, our lambdas. What we can do is take 1 minus lambda, because it's in a column by itself, and cross out its row and column and multiply it by the determinant of what's left. So this determinant is equal to 1 minus lambda multiplied by the determinant of 2 minus lambda, 6, 4, and 4 minus lambda. This is 1 minus lambda multiplied by what? Lambda squared minus 6 lambda plus 8 minus 24. 8 minus 24 is negative 16. We can factor this to be 1 minus lambda multiplied by lambda minus 8, lambda plus 2 is equal to 0. So there are our 3 eigenvalues. We can solve and see that lambda is equal to 1, lambda is equal to 8, and lambda is equal to negative 2. And multiplying all these together, we get negative 16, because all they want is the product of these. So 5 is A. Question 6, we have a matrix A and a potential eigenvector here. We're trying to find the eigenvalue corresponding with this eigenvector. Instead of directly solving for all of our eigenvalues, seeing that they are plus or minus 3i, it looks like, that's how that'll work out, and then actually solving for those eigenvectors, what you can do is solve for this just knowing a graphical fact about the properties of eigenvectors. Along an eigenvector, when we apply a transformation, if this was our input vector for our transformation, if it's along an eigenvector, it will get scaled by a certain value, and it will stay on its own span during that transformation. So it doesn't get kicked off its own span, and the factor that it gets scaled by is our lambda. That is the eigenvalue associated with that eigenvector. So all that means for us is if we take our transformation matrix and put negative I1 in as our input vector, what do we get out? We get 3 and 3i. And this guy is a factor of this thing. If we take each of these entries and multiply them by 3i, we will get negative I times 3i and 1 times 3i. That gives us 3 and 3i. So that means that this guy right here, this factor, is the eigenvalue corresponding with this eigenvector. So we get E as our answer for 6. Question 7, a particular solution of this second order non-homogeneous differential equation has what form? So the two things that we need to collect to figure this one out is our solution to the homogeneous equation, so our characteristic solution. So that will be given to us by solving our characteristic equation, which is r squared minus 9 is equal to 0. That has roots r is equal to plus or minus 3. And so we can write yc as c1 e to the 3t plus c2 e to the negative 3t. There we go. Now the second kind of equation that we need to collect here is our ideal guess for our y particular. So this is our y particular guess. That's just going to be a generalization of what we have in this non-homogeneous f of t term on the right-hand side. So generalizing to e to the 3t, we'll just have some constant times e to the 3t, and generalizing cosine 3t, we will have b cosine 3t plus c sine 3t. Remember that sine and cosine always have to come together in a pair in this context. So now here is our ideal guess. Here is our yc. What we have to do is take every term in our ideal guess that matches a term in yc and multiply it by powers of t until we have no more overlap. And all that means for us this time is multiplying a e to the 3t by t, because we have some constant times e to the 3t here, and we used to have some constant times e to the 3t in here, and multiplying it by t will completely get rid of that issue for us. And that gives us what? That's option C for number 7. That is correct. Question 8, y of t is the solution to this initial value problem. We're finding y at 1. So since this is homogeneous, the only portion of our solution that we need to solve for, well, it's our entire solution, is our characteristic solution. So we need our characteristic equation. That's given by r squared minus 4r plus, r squared minus 4r plus 4 is equal to 0. R minus 2 squared is equal to 0. That has roots r is equal to 2 with a multiplicity of 2. So that means that we can write yc as c1 e to the 2t plus c2t e to the 2t, because remember, when we're writing duplicate roots like this, every additional instance of that root, every additional multiplicity will give us an additional power of t on that component of the solution. So really we're just solving for C1 and C2, and then we'll be able to evaluate y at 1 and we'll have our answer. But for that we need a derivative here. That's 2c1 e to the 2t plus c2 e to the 2t plus 2c2t e to the 2t. Okay, y at 0 is equal to 1. We can plug that in right here, and what do we get? We get 1 is equal to c1. Yeah, that's that's all we get, because this t will make that entire bit of that equation 0. What about this second condition. Y prime at 0 is equal to 0. That says that 0 is equal to, I'll actually write this down here, 0 is equal to 2c1 plus c2, and then this whole bit will go to 0. So since we know that c1 is equal to 1, I'll just replace that here. Since c1 is equal to 1, we can replace this with 2, and then c2 must be equal to negative 2. There we go. So we have our equation for yc given right here. All we need to do is plug in 1 and we'll have our answer. Y at 1 is equal to e to the 2 minus 2e to the 2. That gives us negative e to the 2, so 8 is C, and that's correct. If we're using variation of parameters to find a particular solution yp to this whole thing, we get an equation in this form. We're looking for v1 prime of t. Okay, before we kind of try to think about what's going on here, let's write out the entire formula for variation of parameters. It says that yp is equal to negative y1 times the integral of y2 times f of t over the Wronskian dt plus y2 times the integral of y1 times f of t over the Wronskian dt. Now, if we factor a negative 1 in here, we see that we have something very close to this form if we go and replace our y1s and y2s, but actually we'll need to solve for those y1s and y2s using our characteristic equation. So r squared minus 2r plus 1 is equal to 0. That factors to r minus 1 squared is equal to 0. So we can write yc is equal to c1 e to the t plus c2t e to the t. We will call this y1 and this guy y2. That means we can go substituting in here. Y1 is e to the t, y2 is t e to the t, this y1 is e to the t, and t e to the t right there. Okay, so we have to do a little bit more substitution, but we can actually get rid of a lot of this equation right now. We're looking for v1 prime of t. That's the thing multiplied by e to the t in our solution. The thing multiplied by e to the t is right here. What is the derivative of that? Well, that will just get rid of our integral. So v1 prime is equal to negative t e to the t times f of t over the Wronskian. And sorry I'm kind of half substituting things in and half not at this point. That's just how things ended up working out in my head, so sorry about that. But let's go replace all of these other things while we can. F of t is just this right-hand side term so long as the coefficient on y double prime is 1, which it is. So we can replace that with t to the negative 4th e to the 5t. Now this Wronskian is the Wronskian of our two fundamental solutions. That is the derivative of, the determinant of, our two fundamental solutions and their first derivatives. So we have e to the t and e to the t and t e to the t and e to the t plus t e to the t. Taking this determinant, we get e to the 2t plus t e to the 2t minus t e to the 2t. This just gives us e to the 2t. Okay, so simplifying this down, what do we get? v1 prime is equal to negative e to the 3t, no, not 3t, e to the 4t, and then times t to the negative 3rd power. So I'm getting B, and the answer key agrees. 10. Given that e to the x is a solution of this crazy equation here, which function is another solution? Yeah, and then we're answering with a differential equation. So this is an extremely scary problem because it's one of the only times that they don't make you apply reduction of order directly. They make you actually perform the substitution. Because remember, the nice way to do reduction of order, if we're looking for a second solution, is y2 is equal to y1 times the integral of e to the integral of negative p of t dt all over y1 squared dt. And believe me, this thing is much easier to remember than what we were about to do, because okay, so the substitution that you end up doing here is not fun at all, and so we are not going to do it. We're going to write out the general form of an equation that we can apply reduction of order to, and then the general form of what we get after that substitution. So the substitution that we're doing here is, and I'm not going to pretend that I actually remember this stuff. I have the Wikipedia page open, so that's what we're going off of. Our substitution, or what we're solving, is y2 is equal to some function u of t multiplied by y1 of t, where y1 is just e to the x in our case. And I'll go replace these with x's, since that is our dependent variable. And then what you would do is take the first derivative and the second derivative of this, and they end up getting really big, and then you plug it into this thing, and it's a whole arduous process, but you end up getting, there's a generalized form of what you end up getting every time. So if our equation is of the form y double prime plus p of x times y prime plus q of x times y is equal to r of t, where in our case r of t is just 0, for this homogeneous case, then our solution, and I'll actually leave that r of t in for now, r of t. Our solution, or the substituted form of our solution that is linearized so we can apply integrating factor to it, is u double prime plus 2y1 prime of x over y1 of x plus p of x multiplied by u prime is equal to r of x. Reading t's and trying to write x is a little hard. Divided by y1 of x. So if you really want to remember this, I guess commit this thing to memory, and in fact just go pull up wikipedia.org/wiki/reduction of order, and that will really give you this. It's under general method. It's better to read that off there than off my terrible handwriting, but this lets us solve this question just directly. Note that we have to put things in the form where the coefficient on y double prime is 1. So in order to get p of x and q of x, we have to divide everything in here on both sides actually by x. So that gives us an equation of the form y double prime minus x over x, which is 1, plus 1 over x, which is just 1 over x times y prime, plus 1 over x times y is equal to 0. So here is our p of t term, here is our q of t term, here is our r of t term. So this thing r of t is 0. So in our answer here, this whole thing will also be 0. Then what is p of x? Well, we said, oh no, I wrote t here again. Oh my god. P of x is this thing we said, but we got to factor this negative sign in. See, there's always something with this question. There's so many little things to remember. So there's our p of x, so we can substitute that in here. -1 minus 1 over x. But then we've got this y1 and y1 prime. Well, we know that e to the x is a solution, so that is the fundamental solution that we're working off of to get this second solution. So that will be our y1 e to the x, and the derivative of that is just another e to the x. So this gives us 2 minus 1, so 1 minus 1 over x times u prime. But the thing is, look at our answer choices. It's not there. They went the one extra step to try to confuse us even more, and all we have to do is multiply everything by x. And that gives us, if I remove that thing right there, that gives us exactly a. X times u double prime plus x minus 1 times u prime is equal to 0. Oh, God. Personally, I never had to fully remember this method. Maybe you guys do in 262. I did 266. I really hope you don't. This is not fun. I'm sorry. I'm sorry about all of this. And let's check that answer. 10 is A. 11. Consider a spring mass system satisfying these equations right here. We're dealing with damping. So our general equation for telling if something is damped, or what qualities that damping has, relates c squared with 4km. Now, what are these things? Well, remember that the general form of a mass spring equation is m, and I'm using x here because you see x much more often than you see y. So mx double prime plus cx prime plus kx is equal to, well, we deal with some forcing terms in 266, but I think here we always have it a 0, and in this question, it's also 0. So there we go. If our system is overdamped, then c squared will be greater than 4km. This is overdamping. If c squared is equal to 4km, then we are critically damped. And you see where this is going. If c squared is less than 4km, we are underdamped. And let's find what c squared and 4km are in these cases. But let's go through these answer choices first off. So if b is equal to 0, that's the term on y prime, so that will be c in this equation. If b is equal to 0, I'll plug that in, then the motion is critically damped. Well, what is 4km? M is always going to be 2 in this case, and k is 50. So we can safely always replace this 4km with 4 times 100, so 400. So which one of these camps does this fall into? Well, this is actually underdamped. 0 is a whole lot less than 400. Yeah, so we are underdamped. So this is not critically damped at all. What if b is equal to 12? Is the motion underdamped? Well, if b is 12, then that's that's essentially our b squared here, because they're using b in the position we would usually have c in. And I should be clear, this is our damping coefficient. This this is our spring constant, and this is our mass. I'm not sure why I didn't mention that before. So that just gives us 144 compared with 140, and that is in fact underdamped. Perfect. What about when b is equal to 40? Well, 40 squared is what? Like 16? Is it 1,600 or 16,000? Yeah, 1,600, right? Anyway, what I'm kind of losing my mind here. Yes, it is 1,600. Okay, good. So 1,600 is a lot bigger than 400. So yes, this is an overdamped case. So 2 and 3 are true for number 11. I'm not sure why I chose D. That's 2 and 3 is E. Okay, perfect. Question 12. They're hitting us with a really scary one in the end. We are determining which ones of these are subspaces. And you know what the cool thing is? We aren't going to write anything. This can all be done without solving a thing, and I'll show you how. So S1 is our first potential subspace, and it is x squared plus y squared plus z squared is less than or equal to 1. What does that look like? What does that look like in R3? Well, that's just the sphere with radius radius 1, but it's all of the vectors that kind of make up the interior of that sphere also. Now the thing is, what are our rules for subspaces? Our subspace has to include the 0 vector, which this one does. It has to be closed under scalar addition and vector multiplication. Nope, that's backwards. Vector addition and scalar multiplication. What if you take two vectors that are right next to each other on the very edge of that sphere and you add them together? You're going to get a vector that is no longer in that sphere. You'll get something poking out of the sphere like a little spike. So this thing is not closed under vector addition, and also not closed under scalar multiplication. The only sphere in R3 that will be a subspace is the sphere of radius 0, or the sphere of radius infinity if you want to be cool. Okay, what about subspace 2? We have just kind of 4 equations here. We could make these, or sorry, it's all, yeah, not really, whoops. It's not really 4 equations. It's 4 points in R3 given by this relation here. But this is perfectly fine, right? So we can hopefully make this into a vector, or sorry, not a vector, a matrix of sorts, or in fact a span. Let's do a span. So we could write this as the span of 3 different vectors, an A vector, a B vector, and a C vector, each with 4 entries. So for A, we see that that's involved with our second component. So 0, 1, 0, 0 is our A vector. Then for B, come on, sorry about that. We have 5B in our first component and 3B in our fourth component. So that gives us 5, 0, 0, 3. And for C, where are our C's? We have 2C here, 0, 1, negative 1. There you go. So one thing that you can just solve this by is remembering that literally anything that you can write as a span like this is a subspace. And additionally, if you pick any 2 points that satisfy this, if you pick some random A, B's, and C's twice and you add them together, you'll just get something else that you can express as A, B's, and C's. But really, it's just we wrote it as a span. It's a subspace. It includes the 0 vector. We're good. So this one is all good. What about number 3? We have this equation right here, and it's always scary when we end up trying to figure out whether a differential equation is a subspace. But this one is pretty easy, because what's going to happen here? Well, we're going to have a characteristic solution given by the homogeneous equation, or we'll solve the characteristic equation to find it, and then we'll have a particular solution. The homogeneous solution, yc, will have constants that we can vary around attached to all of our terms. But what's wrong with our particular solution? Our particular solution does not have constants on it. It's fixed. So we might get a particular solution that has like 2 sine t in it. What's wrong with that? Well, if we choose 2 members of this set and we add them together, what should we expect? That we get another entry of the set. But the problem is, and that's the 3rd time I've said what the problem is, because it's a huge problem. Every single member of this set will have 2 sine t in it. If that is part of the particular solution. But if we add 2 of them together, 4 sine t. That doesn't match anything in our set, so that's no good. Essentially, what seems to be the rule is if you have a non-homogeneous second-order differential equation, so something with a particular solution that does not have constants on it, that equation there will not be a subspace because it will not be closed under vector addition. Likewise, for the same reason, this equation right here is perfectly fine. We don't even have to solve it because no matter what this characteristic equation solves as, it will end up with constants in front of all of its terms, which means that it will obey the kind of the laws that we want it to obey. It will be closed under vector addition because those constants can adjust for whatever kind of adding or subtracting we're doing, and those constants can go all the way to infinity and negative infinity so that it's closed under scalar multiplication. Now finally, number 4 is a pretty complicated looking polynomial subspace, but the thing is, and you can test this for yourself with some values for a and b if you don't believe me, this works perfectly fine under vector addition and scalar multiplication. And in general, if you just have coefficients formed from these kind of linear terms where we don't have any constants a and b squared or multiplied together, you have absolutely nothing to worry about as long as everything stays linear like this. So that can be something to look for in the back of your head, and this one works perfectly fine. All of them can be equal to 0, so we'll get the 0 polynomial, so that's a check mark, and you can check scalar multiplication and vector addition on your own if you really feel like it. So that gives us 2, 4, and 5, and A is our correct answer for number 12. And we are done. Yeah, okay, see ya.